I'm very excited to share with you my recent work with Jeremy and Eric on quantum symmetry and geometry in double-scaled SYK. Double-scaled SYK is a solvable model where arbitrary correlation functions of this model can be evaluated by the so-called chord diagrams. Here is an example. To evaluate the correlation function in the left-hand side, we draw a disk and we draw the insertions of these operators in order on the boundary of the disk. And then we sum over all the possible weak contractions of the boundary insertions. A given chord configuration is depicted in the diagram here, where the diagram contributes to this correlator by a number. And the number takes into account the penalty factors associated with each coursing. And the penalty factor is generally a real number that ranges from 0 to 1, which will not be important for today's talk. Later, a Bulk-Hilbert space has been associated to this description, where the summing over chord diagrams can be viewed as can be understood as taking the inner product between open chord states living on a Bulk slice. The inner product is defined by summing over the chord diagrams. The model has since been explored with its rich geometric and algebraic structures. However, it remains unclear why the quantum 6J symbol appears in the calculation of coursed four-point function. So today, we uncover the underlying quantum group structure relevant for the quantum 6J symbol. We begin with one particle Hilbert space specified by the one matter insertion in the bulk with some amount of Hamiltonian chords inserted to its two sides. In an earlier paper by me, I find the energy eigenstates that diagonalizes the left and the right chord Hamiltonia. With this basis, it's very straightforward to realize the unitary equivalence between the one particle Hilbert space living on the bulk with the two copies of boundary zero particle Hilbert spaces that can be viewed as living on the slice in the bottom. One can think of states in the double Hilbert space as operators acting on the original zero particle Hilbert space. And in particular, with this set of states, we find a curious recursion relation reminiscent of the discrete series representation of the quantum group uqsu 1, 1. The quantum group is just a associated algebra generated by four generators subject to the following commutation relations. In our paper, we are able to reconstruct these four quantum group generators completely from chord algebra generated by left and right chord creation and annihilation operators. In particular, we can perform a spectral decomposition with respect to a self-adjoint element of the quantum group, such that it leads to a decomposition of the one particle Hilbert space into the irreducible representations of the quantum group. And we can move on by building up the multi-particle spectrum of double-scaled SYK with the help of a coproduct structure of the quantum group. The coproduct structure determines how the tensor product of irreducible representations decompose into irreducible representations of the quantum group, essentially the fusion rules. And the R matrix in this context appears as a swapping operator that swamps the order of fusion carried by two matter chords. So in this context, the takeaway of this study is that the quantum R matrix appears as completely determined by the fusion rules and the coproduct structure of the quantum group. Here are some future perspectives. We find a novel factorization formula, and it will be very interesting to understand its boundary interpretation. It will be also very interesting to understand the quantum group structure in the dual description of double-scaled SYK. and whether the submaximal chaos can be explained by a modular chaos associated to the fake disk. Thank you for your attention.